recording. Okay.
The ladybug.
Right. Now the PowerPoint, so I can go to the PowerPoint individually, call up the PowerPoint top there, just minimize the PowerPoint and go back to there.
Yeah.
That's what I need.
And this is the button for if you want to continue writing or recording. That way you don't have to like.
How do I undo it from full screen?
Oh, the button shows up. They make it nice and easy. It doesn't go away when you're watching a movie.
Got it.
It stays there. And this one's way
So
better.
good.
It's HD video and there's no latency. So
Thank you. Thank you. Thank you.
See, I knew you would want that old one
You the
back.
man. You the man. All right. You can take the dinosaur back if you want.
And there's some cool things here. You can also zoom in and zoom out here. You can turn off the limb. It has a balance, and you can also take pictures with it too. So if you're writing something and you want to capture it, it'll actually save it to your computer while you're doing it.
Okay, that's too fancy right now.
Too fancy?
But I'll work on that.
Work on it? Okay.
It's nice. It's everything the other one
Thank
was.
you. I know you are the man. You are the man.
It's with me and I'll log out of this registration.
Thank you, thank you, thank you. Okay. Woo. And almost in time too.
Here, let me finish up this. This is the instructor station has it for
We'll
me.
change place. Or we can change
Yeah,
it.
sorry. And there we go. Super quick.
Make sure that's good. Source, playback. Okay. And ladybug will work it just as good.
Okay, I think you're all set. Don't be
Thank
afraid to give us a call
you.
though.
Thank you. Do you guys know what section we are today? Where are we? What section are we? Of the choices here. We want to start putting this up here. Make sure you have this on your radar screen. So, what are we? I think we probably are because it's Wednesday, right? And this is the honors. Okay, so yeah, that's us. So our final is Wednesday, May 10th. At 9 a.m. So that's different than our class time. Common misconception amongst first year college students is that the final for the course is at the same time as the final for the lecture. And that's not true. I don't choose the times. Admin chooses the times, and what they do is they want to make it so no times overlap, right? So that you don't have a final, one class doesn't have a final at the exact same time for students. So that's why they set this. I don't set this. So it is 2 hours. If you guys don't show up till 10, thinking that it's at 10 instead of 9, you're going to waste a whole hour and I can't give that hour back. So make sure that you know that that's the case, because we've got today and then we got 2 more weeks of regular class and then we're done with class. Right? All right, so today we're going to finish chapter 11. We're going to take the chapter 11 quiz. That takes about 45 minutes. Then Monday we'll cover all of chapter 13. Wednesday we'll take the 13 quiz and cover the majority of 10. And 10 is all about gas laws. And then this day we'll take the 10 quiz. I'll briefly mention the 12, I think it is, the one about solid structures, the smidgen of 12 that you need to know for the final exam. And then your Unit 3 exam will be that last day of class, which is Wednesday the 3rd of May. Now, because we are a smidge behind, what that doesn't allow me is time to give the exam back to you so you can take a look at it, plus ask me any questions about that, if why things were wrong, so that you can get feedback. It's important to have feedback. So what I generally like to do is on that Friday, let's say 10 a.m., I'll get a room, and those who want to, you don't have to, certainly, but those who want to can come on this day at 10 a.m. and I'll announce the room when I get one, etc., etc. And at that point, then I'll give the Unit 4, did I write 4? Oopsie, got the wrong unit. Unit 4 exam, I'll give that back to you at that point, so you can look through it, see what you got right, see what you got wrong, because that's important to get that corrected in your brain prior to going into the final exam. The final exam then is this day. Remember, this is the ACS final. You need to bring your own Scantron. There's 66 questions on the final. They are difficult. Okay. There is a practice final posted on Canvas. And students ask me every year, how much is the practice final like the actual final? And my answer always is, I don't know. I don't know which final I'm going to give you until the morning of my final exam when my department chair hands me the package of finals and says, here's what you're given. Okay? So I don't know. The practice final was written by a teacher from this school about 8 to 10 years ago. So keep that in mind too. And he was actually a really good person to write this review because he used to grade AP final exams in, I think, Boston or DC, one of the two, at the end of every school year. That was one of the things that he liked to do, and they paid teachers to do that. College chemistry teachers to go and grade AP high school exams, the essay questions of them. So he was a good person to write the review. There's a review and then there's an answer key. And the answer key has the writing of the teacher that wrote the review on it and how to solve the problems. That's not necessarily how I would solve the problems. That might not be how you solve the problems, but that's how he solved the problems and shows how the answer was derived. Okay? So what I would do if I were a student in this class, if you want to use that as a practice final or as sort of a test or an assessment for yourself, is sit down with the exam and take it in the same conditions that you would take it in this class, the conditions that you'll have in this class. You will not be able to use a 3x5 card. Okay? You will get that sheet that they give you on the practice exam that summarizes the basic big picture algorithms like density is mass over volume, right? And 1 cubic centimeter of water is 1 gram of water. You know, those kind of basic things are on it, plus the periodic table. So that same exact sheet that is on the practice exam is the same exact sheet you will get when you take the ACS final. And they allow us to let you guys see that beforehand so that you know what reference and resource you're going to have. Now, if I was doing this class, I would certainly know solubility rules. The big picture one's in my head, right? Because you can't have a 3x5 card. And then there's some other things that you might think of as you're going through and reviewing everything. A good spot to review is at the beginning of the syllabus. There's a list of what's called the course competencies. And course competencies means what we all agree on, the teachers of this course, as to what should be the things that are taught in the class. And this is for what's called articulation purposes. Articulation means when you take this class, Gen Chem 1 here at this school, it transfers to any public institution in the whole United States as first semester Gen Chem. And we all agreed, all the chemistry teachers, all the colleges, all the universities across the whole United States, we agreed on these what are called common course competencies. So if you look through each of those 28 listings of stuff you need to learn how to do when you take this class, those are the things that the ACS will assess you on. So the practice exam is a good way to self-assess. This list is a good way to self-assess. And once you take that practice exam, then take the answer key after you finish the whole exam and sit and grade your own exams, right? And then look and say, oh, I'm doing really good with stoichiometry, but over here with naming ternary acids, I forgot how to do that. I'm going to write a note to myself, and on that review day, on that Friday, I'm going to bring my note to class, or my notes to class about certain questions, because on this day, when I return your exam, and I'll schedule a 2-hour block to review. All right, so we'll have 2 hours together. I'll give the exam back. You can ask those questions. I'll collect the exam back up. And then we'll do a general course review. I'm not going to have a review prepared because in order to summarize an entire 15-week course and summarize it in 1 hour is basically impossible. All right? So what you should do is have specific questions. As you start to review, as you're wrapping up your knowledge base for this course, make notes to yourself about things you'd like to review. And then when you get to the review, you go, hey, remind us about ternary acid nomenclature. I forgot that. So, well, absolutely, ternary acid nomenclature. So specific questions are good. If everybody just shows up with like an empty vessel and sits in front of me, then we're done. So you need to have specific questions. I'd be happy to stay the entire 2 hours or even more if we have space in the room, as long as you all have specific questions. Okay? All right, so that's how we can accommodate the fact that we've got to take our exam on the last day of class, and then you at least get time to get the exam back, look over it, get some feedback. That's what. All right, so let's finish. Now they messed up the projector, so I'm working with a new projector, so you guys gotta be patient. Yes?
I do have one more question about
Sure.
that one homework question.
Okay.
Um,
Okay, let me review for everybody, Ariana, what the homework question
Okay.
is. Some of you that have started the homework, and I think, is it due tonight or was it?
Yeah.
Okay. It's due tonight, the Chapter 11 homework. In the Chapter 11 homework, there is a question, and it says that hydrogen bonds are not as strong as,
it's ion dipole are the first ones.
okay, that is, okay, I don't want to say it's wrong, but it certainly is against what my impressions are of hydrogen bonding. Okay, there are certainly differences of opinion in and within the scientific community all the time, but hydrogen bonding is generally accepted universally as the strongest type of intermolecular force. So, take that. I will not give you a question like that that says, is hydrogen bonding the strongest or the weakest, and not have the answer that we've discussed.
Okay, I was just wondering about the final two. If we should go with that answer.
No.
No.
No, ACS definitely agrees with me
Okay.
and with those more that hydrogen bonding is the best
Okay.
type.
Okay.
I should really do something with that to mastering chemistry and submit a question as an instructor and say, hey, so if you guys have that question number and what it is, just send me a little quick email that says the question that we're talking about is question blah, 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 so I know. It's a sorting one. I know you have to like drag and drop the things into boxes. All right. All right, so let's start and finish chapter 11. And you guys have to remind me where we left off, because I know it took me longer to get going with you guys because we were suffering under the same issues as this. Did we get to this slide and talk about surface area and molar mass? Did we talk about this slide yet? Don't think so? All right, let's back up a little bit even more. Did we talk about...
This is where we stopped.
We did, I think so. I think I recall this. We talked about the weakest, the wimpiest type of intermolecular forces, which is this idea of London dispersion forces. London dispersion forces happen in particles that are nonpolar. Right? So if it's polar, so here's kind of a flow chart you can think about. If the first thing you look at in a molecule is it polar or nonpolar, right? If it's polar, what are the types of bonds that can happen if it's polar? Hydrogen bonding, what else? You can have dipole, dipole, or ion dipole, right? Okay, we'll summarize. So nonpolar, it can have London dispersion forces, right? I'm going to abbreviate those. So if we're talking about a nonpolar molecule, something that doesn't have an unequal distribution of charges in and of itself, it can get that unequal distribution one of two ways. Either the way the electrons are spinning. Can we talk about this on Monday, the way the electrons are spinning in this motion? Don't remember? Yeah, kind of, sort of. Okay, so that's how you get a temporary dipole. So what happens here is a temporary dipole. Right, so temporary dipole, because these are all polar things. So this is the nonpolar thing, so a temporary dipole can be created one of two ways. Either the electrons spin, and when they're spinning, they get next to each other at some point in their spin, right? Or the idea of bumping. If you have something like a 5-carbon long chain hydrocarbon, 1, 2, 3, 4, 5, that's methane, ethane, propane, butane, pentane. All right, so this is what, and this is in the next slide too. Organic chemists really did a good job with their nomenclature. It makes a lot of sense once you learn how to do it. So those of you that got to take organic chemistry, you can embrace the nomenclature. This is called normal pentane. And the number of carbons dictates the base name of the compound. Methane is 1 carbon, ethane, propane, butane, pentane. So this is normal pentane, meaning it's a straight chain hydrocarbon. If we get normal pentane or even butane or propane, see methane, ethane, propane like in your barbecue grills. Propane is a smaller, shorter, straight chain hydrocarbon. This is propane. If you get propane in one of those propane jugs and it's in liquid form, and it's just exclusively propane in there, those are definitely both nonpolar molecules. What happens is one propane will bump into another propane, And normally the electron cloud looks fairly even because it's nonpolar, but when it bumps into another one bumps into another one, it causes a temporary distortion of the electron cloud for a moment in time. And so this side would be slightly negative because the electrons were distorted. This side would be slightly positive, and only in a temporary nature. So collision idea. Remember, most of these types of intermolecular forces take place in liquid form. The molecules have to be relatively close to each other, but yet free to move around in order for the magnetism or the forces that they have in between them to influence their attraction for each other. All right, so here's one that we can call the normal pentane versus neopentane. I should be drawing this on the projector here so that we can tape this good stuff. All right. Look at normal pentane versus neopentane. Normal pentane is the 5-chain hydrocarbon. That's not very easy to see. The light's kind of bright. Does that look better? Yeah. The light out of the way. All right, this is normal pentane, like on the slide, and neopentane still has 5 carbons. But they're hooked together not in a straight chain. It still has the same number of hydrogens. Now I'm not going to draw the individual bonds here, I'm just going to draw where the hydrogens are. So you get the idea, right? And it's still 1, 2, 3, 4, 5 carbons, C5, and then there's H3, 6, 7, 8, 9, 10, 11, 12. All right, they both have the same molecular formula or chemical formula and the same molar mass. But which one do you think would be more likely to be, and they use this term in your textbook and in the homework, more polarizable? Which one of these two would be more polarizable, normal pentane or neopentane? Normal would, because it's got a longer surface area here. So if the electrons are imbalanced, right, the normal electron cloud would look something like this. If the electrons are imbalanced, it's going to create a greater difference here. So this is going to be negative, this is going to be positive. If this thing is in a container that bumps into each other, the normal electron cloud is like this. It's much more compact, less surface area, right? So when it gets misshapen, it's not going to be as much of a difference. So this is one we call more polarizable. So if it's more polarizable, it has a larger temporary dipole. Which one of these would have a higher boiling point? Normal pentane or neopentane? Normal pentane would have a higher boiling point. And why would that be true? Why would it have a higher boiling point than this one? Well, more surface area, and it can become more polar. So if it's more polar, just even for a temporary moment in time, it will cause the molecules to like each other more, right? And it's going to be more difficult to change it from a liquid into a gas. All right, let's think of vapor pressure, right? Vapor pressure. Now, vapor pressure, let's have a quick discussion of vapor pressure first. We have a closed container. And in my closed container, I have a substance existing at both liquid and gas phases, right? So I'm going to put some little dots in the gaseous phase, right, to represent the fact that I've got some particles of gas in the gaseous phase. What's going on here is there's some liquid that's changing into a gas, right? It's evaporating. But because it's a closed container, there's also some of the gas going back into the liquid, and we call this equilibrium. So there's an equilibrium going on in this container. If I could put a pressure gauge on the outside of the container and simply look at the air pressure that is above the liquid, that's what we call the vapor pressure, right? The pressure of how much vapor you've got that exists in this closed container that has both liquid and gaseous phases in it together. So let's think about this idea of pressure just for a moment, because we haven't talked about gas laws yet. What actually causes pressure? physicists have a really good definition of pressure.
Movement of the atoms.
The movement of the atoms. What happens when they're moving that causes pressure? They hit each other, right? They also hit the sides of their container. So anytime they hit each other or hit the sides of the container, that is measured as this idea of pressure. So if you increase the pressure, that means you're increasing the number of collisions between the gaseous particles in this portion of the container. If you decrease the pressure, the opposite is true. You're decreasing the number of collisions. So we could measure that with a pressure gauge. And pressure is measured in things like millimeters of mercury or ATMs. There's a whole bunch of different variations of pressure. So let's think about the types of variables that would influence the pressure of the vapor above the liquid in a closed container like that. All right, what variables can I introduce into this situation that might either increase or decrease the pressure of the vapor? Volume, absolutely. So maybe I have a container that I can make get bigger, right? And so now I have more airspace available to me, right? So what would happen to the pressure initially? The pressure would go down, right, because I have more airspace. Okay, what else could I do other than increasing or decreasing the size of the container? Temperature, absolutely. I could put on a hot plate or cook it a little bit, right? What would that do to the pressure of the gas particles that are above? Increase it, because they'd start moving faster, right? The ones that are already there would start moving faster. But also, what would happen to this equilibrium if I increase the temperature? I'm going to get more going in this direction, right? So I'm going to make the arrow darker in that direction. This would still be happening, but at a lesser rate in comparison to the increase that temperature causes that to happen. So overall, more would leave the liquid phase, right, and turn into a gas. All right, now let's think about intermolecular forces. Things like water that has hydrogen bonding. So say, for example, I have two different containers, and they have different substances in them. Say I have water, and say I have ammonia. And I have both containers have liquid and gaseous phases in them, right? So I've got an equilibrium going on in both containers. If they're at the same temperature and the same amount of volume and the same initial amount of gas, which one would have a higher vapor pressure? Let's look at the Lewis structure, right? That's helpful. Bless you. Which one of these is more polar of the two? Okay, this is more polar, right? Why is this more polar? Two non-bonded pairs. They both have hydrogen bonding, don't they? Our definition of hydrogen bonding includes in the fact that you have to have hydrogen connected to what three atoms, potentially? Nitrogen, oxygen, or fluorine, and that's because those are the most electronegative, right? And that creates a bigger dipole. So this is going to be more polar. This is going to be less polar. It's still going to be polar, right? Now I'm going to ask you, which one's going to have a greater vapor pressure? This one. Why is this one going to have more molecules up there? Why is there going to be more molecules in the NH3 compared to the H2O? It's less polar, right? They like each other less. So it's easier to make that transition from liquid to gas than it is for water, which is more polar, and so the molecules like each other more, right? So that's the idea of vapor pressure.
So you said the NH3 has greater vapor pressure?
The ammonia would have a greater vapor pressure than the water, because ammonia is less polar, water is more polar, water is more likely to, it's like if I had, okay, water would be the magnetic pieces, right, that are really strongly magnetic in a box, and then the ammonia would be the less magnetic pieces. It's harder to pull a really magnetic piece out of the box than a less magnetic piece. All right, here's a good example. Between these two, between normal pentane and neopentane, which one would have a greater vapor pressure? Keep it in mind, and we have to have liquid and gas in the same container in order to have this vapor pressure. right? So which one would have a greater vapor pressure? The neopentane. And we would say the reason why is because less surface area and it is less polarizable and has a weaker temporary dipole. Right? So we're using significant vocabulary from your homework there. All right, if we look at things that are also nonpolar, like the halogens are all nonpolar, fluorine, chlorine, bromine, iodine, they're all diatomic gases at room temperature. And if you look at those, what happens to the boiling point? Goes up. Well, if they're all nonpolar, why does the boiling point go up between fluorine and iodine? Well, yeah, that's true, greater surface area, but there's a bigger factor than surface area than this involved. Molar mass, right? You got some really beefy molecules. Iodine weighs, holy capoly, like 150 something grams per mole, where fluorine weighs, what, like 39, 38 grams per mole? Big difference. You got something that's really big, it's going to cost you a lot more energy to vaporize it, but it's also more polarizable, right? It's got more electrons, so there's two factors there. Same thing here with the noble gases. As you get heavier and heavier, you get more electrons. More electrons are more polarizable, so the boiling point of those things goes up. And there's a summary of the intermolecular forces in flowchart version if you are an engineer or a computer programmer and you like flowcharts, right? So those are the people that like flowcharts. So there you go. Intermolecular forces also affect this idea of surface tension. Surface tension you see when we see bugs sitting on the water. I used to live in a house with a pool years ago, and we would see these critters. We called them, the boys call them boatmen, I think. I've also heard them called oarsmen. These critters sit on the surface of water. They're taking advantage of the surface tension of water, which is caused by the water molecules' differences in the pull. So if you're looking at a water molecule in this beaker, and the water molecule's down embedded within the context of all the water molecules surrounding it, you can see that they've got lines that show the forces that are attracted to that individual molecule smack dab in the middle. And you can see that the forces are pulling evenly all the way around that molecule, right? The one that's down in the bottom of the beaker down here. If you look at a molecule above in the top of the beaker, only forces are pulling to side, but only also pulling down. There's no forces pulling in the up direction here. And so what that does is it creates a situation where the molecules are actually a smidge closer to each other on the surface of a liquid, right? So if I could exaggerate here, surface tension creates, and this is of course a huge exaggeration, right? So we got surface tension is created because the molecules are a little bit closer to each other. They call it a skin, right? Sort of like you put saran wrap over it. You know how saran wrap works? You know, if you took something sharp and you poke the saran wrap, of course it'd go through, but it has this kind of a force. And if you've ever looked at water, if it's in a glass container, it will cling to the glass. But if you look at water and you put a drop of it on a piece of glass and you look at it and you put it on the side, it actually makes like a little round ball like that. If you take you take a glass plate and you put a drop of water on it, and then you turn the glass plate up on its side and the water droplet will move down to the bottom, it will create little drips like this, but then it'll stop and it reforms this whole surface tension. If you took a drop of alcohol, which is less polar, it's still polar, this would be water, this would be alcohol. Alcohol is still polar, but not as much as water is, so it still has a skin, but it won't make a nice round droplet like this. And if you take a droplet of alcohol, it will drip down, but it also leaves a lot more bits as it travels. If you took a drop of oil, which has no intermolecular forces except for London dispersion forces because oil is nonpolar, right? It spreads out real thin on the surface, and if you turn that to the side and let the oil drip down, it would drip down significantly quicker once it reached that, level of angle that caused it to move down. If you looked at the evaporation of these, which one of these, if I allowed a drop of water versus a drop of alcohol to sit out in room temperature, which one would evaporate first? The alcohol would evaporate first. Which one would have a higher vapor pressure? The alcohol would have a higher vapor pressure, right? We know that. I could take a drop of isopropyl alcohol in the classroom here, put it on a little watch glass of glass, and people in the front would start to smell it right away, right? Because the pressure of the vapor. Vapor pressure is also apparent if you are in Arizona, specifically in the months between October and March. All gas stations in the Metro Phoenix area have to have a vapor locking device as you're putting gas in your car. Have you seen those? It's kind of an extra thing that sort of fits around the handle, and as you put the gas nozzle in, it kind of comes around and covers it. But what that's doing is it's not allowing the vapor of the gasoline, which has a very low boiling point, right? Gasoline is very non-polar, so it evaporates very readily. Can't you smell it? If you drip a little bit out of your car, can't you immediately smell it? Okay, it has a very high vapor pressure because it's not polar at all. But what happens is they didn't have that vapor lock on there, and you're putting your gasoline in your car, a lot of it is vaporizing. Say, for example, I'm a millennial who can't get by without my cell phone for 10 minutes, right? Teasing you millennials, so I raised 2 of them. All right, so I'm a millennial, I can't get by without using my cell phone for 10 minutes, and I'm gassing up my car, and I open my cell phone, I dial something and press send. As I'm gassing up my car, and I don't have that vapor lock device, and all that gas is vaporized, and I got a high vapor pressure around me, and all of a sudden my cell phone makes a spark. What's going to happen? Okay. So in Arizona, that's why they insist on putting the vapor lock between those months, because we add ethanol to the gasoline to help it burn cleaner and burn hotter. That ethanol also increases the vapor pressure, makes more of it vaporize, makes it more dangerous for you to be on your cell phone while you're gassing your car. Okay? I'm at the gas station all the time, and I see millennials doing that, and I'm always debating, do I step in and say something? And I go, where's this crazy old lady telling me not to use my cell phone while I gas up my car, right? Or do I just hurry up and gas up my car and get the heck out of there? Right. Okay. I usually choose option 2 because I don't like to be a meddling old lady. But I find as I go out to lunch with my mom, who's 86, that once you get to a certain age, you can say or do almost anything, and people are very forgiving. Right? Have you noticed that? Do you have grandparents? You take them out, and they say something, completely embarrassing, and you're like, oh my gosh, Grandma. People are like, it's okay. Like, we get it. All right. Back to the PowerPoint. Enough about my mom. All right, viscosity, resistance to flow. We used to do a cool experiment when I taught high school chemistry that kind of showed this. We would take a test tube and put different non-polar substances in the test tubes. Like we would have regular gasoline from a gas station. We'd have gasoline, we'd have kerosene, and we would have like cooking oil, which are all non-polar substances, and they're all long-chain hydrocarbons. Some of them would be shorter, some of them would be longer. We would fill the test tube completely up with that substance. Then we put a marble at the bottom of the test tube, and we'd seal the top of it with plastic so it wouldn't leak or anything. And then I'd have the students take, and they would turn the test tube upside down so that now, when it's upside down, the marble's here, the marble will eventually fall. And they could time the amount of seconds that it took for the marble to fall. And that was a good measure of what we call viscosity. And viscosity is the resistance to flow. All right, so think of the vocabulary word viscosity being the resistance to flow. So if I've got molasses in North Dakota in January, is it going to have a high viscosity or a low viscosity? A very high viscosity. I take that molasses to Arizona, and now it's not January, it's July. Do I have a high viscosity or a low viscosity? I got a low viscosity. It's going to flow all over the place, right? In comparison to what it did in January. So viscosity is influenced by intermolecular forces, as you might expect. And as the molecules get bigger, here are long-chain hydrocarbons, right? Hexane, heptane, octane, nonane, decane. Hexane is a 5-chain hydrocarbon. Decane is a 10-chain hydrocarbon. Which one do you think would have a higher viscosity? Which one would be more resistant to flowing? The longer chain hydrocarbon. Why the longer chain? More surface area, right? You got a long chain hydrocarbon, all full in a container. They're all like this, right? You try and pull one of those out, or you try and get a marble through a long chain hydrocarbon that looks like that. You got a short chain hydrocarbon. They only can hook like that. It's much easier for the marble to go through. Right? So you got to think about the way that viscosity is influenced. And finally, we talk about phase changes. We're not going to do a lot of the math because we already did that in chapter 5. We did the math, so woohoo, we don't have to do that. But I do want you to take a note of this particular phase diagram, solid to liquid, liquid to gas. If we look at this vertical axis, it's the energy of the system. So let's describe these in terms of endothermic versus exo. Going from solid to liquid, we call that melting. Is that endo or exothermic? Endo. We had to add energy into the system, and we know because the product, the liquid substance of whatever we melted, is at a higher energy level than the solid. What I'd like you to look at here is, here's the energy endo requirement for solid to liquid. Look at this giant comparison here of this endo requirement to go from liquid to gas. Why do they make it such a much bigger jump here than here? What influences this jump other than that last mode of motion? Temperature influences it, yes, but besides temperature, what could make this jump bigger that we've talked about in chapter 11?
Surface tension.
Surface tension or intermolecular forces of any kind, right? So if you got intermolecular forces, the more intermolecular forces you have, the bigger that difference right there is going to be, right? Because intermolecular forces exist in liquids. And so if you got stronger intermolecular forces, that's going to cause that difference to be larger. Well, let's look here. Butane, which is a very non-polar molecule, right? C4H10, like the butane in your lighters, versus water, which is a very polar molecule. Here, the energy difference between the heat of fusion versus the heat of vaporization is a 5 to 24 ratio. Let's look at the difference in heat of fusion versus heat of vaporization from water. It's a 6 to 41. So what could we infer between those two things, 5 to 24 versus 6 to 41? Which one has more intermolecular forces? Water does, and that's why it's a bigger ratio between heat of fusion versus heat of vaporization. And there's the energy changes. And we've talked about vapor pressure already. This chart is interesting because we've got, as temperature increases, this is the vapor pressure, right? So if we had our closed container, and we got liquid and gas existing simultaneously in the same closed container, right? We have vapor pressure. Which one of these has the highest vapor pressure? Diethyl ether, ethyl alcohol, or water, which is the first 3 lines. Which one has the highest vapor pressure? The ether. Okay, so that's because the vapor pressure increases much more rapidly with increasing temperature, right? What's the boiling point of diethyl ether? How do we know that that was true other than the fact that I moved the cursor over there?
The little line that says normal boiling point.
That helps too. Okay, what else besides those 2 keys that are super obvious? What's that? Well, that's why. But how do I know that that's the boiling? How do I know that besides if that label wasn't there, that the boiling point of diethyl ether was 34.6, 78.3 for ethyl alcohol, and 100 for water?
Oh, the 760.
760. Okay, ding. That was what I was looking for. The 760. What is that number? Pressure of what?
Sea level.
Atmosphere at sea level, right? Normal atmospheric pressure, and then the caveat is at sea level. So that's the boiling point at sea level, and we all know boiling point changes depending on elevation, right? Okay, so if you have to look at this graph, who has the highest boiling point? Water. Who has the highest vapor pressure? Diethyl ether. You can tell both of those things from this graph. And we don't have to do phase diagrams in here anymore. Your 152 teacher gets to teach you that. So, we are done. Take out a piece of paper for a quiz.